Differential equations. Friends, today we will talk about differential equations. Let me introduce you to the topic. Suppose there is a functional relation between x and y, which can be represented as y is equal to x square. This will be our first equation, where x is less than equal to 3 and greater than equal to 0. In this equation, x is the independent variable and y is the dependent variable. The derivative of y will be dy by dx, which is equal to 2x. This is our equation number 2. Thus, for x equal to 2, dy by dx equal to 4, which is the slope of the curve at the point 2, 4. For x is equal to 3, dy by dx equal to 6, which is the slope of the curve at the point 3, 9. Now, suppose we have an equation such as 2, which directly assumes a functional relation between x and y and includes x, y and the derivative of y with respect to x. Such an equation is called a differential equation. So, we can say that a differential equation is any equation which contains derivatives, either ordinary derivatives or partial derivatives. Differential equations can be broadly classified into ordinary differential equations and partial differential equations. The ordinary differential equations are those having only one independent variable and its derivatives. When the differential equation has several independent variables, then the derivatives become partial derivatives and we have partial differential equations. An ordinary differential equation is said to be linear if the dependent variables is of the first degree, that is, the y variable and its derivatives are of the first power only. In this case, the y variable and its derivatives are linearly combined. Now, friends, let us have a look at the general form of a linear differential equation, which is HOX d raised to power n y by dx raised to power n plus H1x d raised to power n minus 1 y by dx raised to power n minus 1 plus so on plus h n minus 1 x dy by dx plus h n x y, which is equal to f of x. This is an ordinary linear differential equation of order n. If the coefficients of y and its derivatives, that is h(o)x, h1x so on till hnx, are all constants, then it is called a linear differential equation with constant coefficients. Let a0, a1 till an be constants, then a0 d raised to power n y by dx raised to power n plus a1 d raised to power n minus 1 y by dx n minus 1 plus so on plus a n minus 1 dy by dx plus a n y is equal to f of x. If f of x is equal to 0, then we have a homogeneous linear equation with constant coefficients. Classification of differential equations. Number 1. Nonlinear differential equations of the first order and first degree. Under this, we have category A as variables are separable case. Case B, homogeneous differential equation. Case C, exact differential equation. Point 2. Linear differential equations of the first order. Under this, we have case A, which is homogeneous differential equation with constant coefficients. Case B, non-homogeneous differential equation with constant coefficients. Case C, which is the general case. Point 3. linear differential equations of the second order with constant coefficients. Now let us look at the nonlinear differential equations of the first order and first degree. There are some special types of nonlinear differential equations that can be solved, which are of the first order and first degree. For instance, dy by dx is equal to f of x comma y. We can understand this type of equation with an example. For example, dy by dx is equal to 3xy square. In differential form, it is written as f1 xy dx plus f2 xy dy is equal to 0. Let us consider case 1, when variables are separable. In the differential equation dy by dx, which is equal to f of x comma y, we can put the equation in the form of f1x dx plus f2y dy is equal to 0. This is easy integrals because we can associate a function f1x with dx, which is only a function of x, and with dy we associate a function f2y, which is only function of y. This is the case of variables separable. Now let us consider case 2, differential equation with homogeneous coefficients. If f xy is a homogeneous function of degree n, then f lambda x lambda y is equal to lambda raised to power n f x comma y. If the differential equation f1 xy dx plus f2 xy dy is equal to 0 has homogeneous coefficients, that is, if f1 xy and f2 xy are homogeneous functions of the same order, then by change of variable we can reduce it to the variable separable case. If f1 and f2 be of order n, that is, of the same order, now suppose y is equal to vx and dy is equal to v dx plus x dv. Then f1 x comma vx dx plus f2 x comma vx into v dx plus x dv is equal to 0. Here we can see that f1 x vx divided by f2 x vx whole into dx plus v dx plus x dv is equal to 0. Since f1 and f2 are homogeneous functions, we can divide out the x. Thus, f1 into 1 comma v divided by f2 1 comma v plus v whole dx plus x dv is equal to 0. And hence we have the variable separable case, which can be solved by integration. Let us now consider case 3, exact differential equations. Consider a function f x y which is equal to x square y. The differential of this function is df is equal to delta f upon delta x dx plus delta f upon delta y dy, which is equal to 2xy dx plus x square dy. Assume pxy is equal to 2xy, where qxy is equal to x square. As we know, delta p by delta y is equal to fxy is equal to 2x, which is further equal to fyx equal to delta q by delta x. Now we reverse the procedure. We are given an expression 2xy dx plus x square dy, or pxy dx plus qxy dy as our equation number 1. If the following conditions hold by the expression, then this expression is said to be the exact differential of some function f x y. Now we see that delta p by delta y is equal to delta q by delta x, which is delta p by delta x is equal to delta by delta y 2xy equal to 2x. Delta q by delta x is equal to delta by delta x square equal to 2x. Thus the condition 2 holds, and we know from 1 is an exact differential of some function f of x y. Let us now set equation 1 equal to 0, that is pxy dx plus qxy dy is equal to 0. This will be our equation 3. Hence, 2xy dx plus x square dy is equal to 0. This is called an exact differential equation. Now friends, let us have a look at linear differential equations of the first order. Let us now discuss about linear differential equations. The general expression is dy by dx plus py is equal to q, where p and q are functions of x or constants. The general solution for this equation is given by y is equal to e minus integration of p dx integration of e raised to power integration of p dx into q dx plus ce raised to power minus integration of p dx. This will be our equation number 1. Now let us consider a case. Case number 1, homogeneous differential equation. When q is equal to 0 and p is a function of x, we have a homogeneous differential equation, and the solution is y is equal to ce raised to power minus integration of p dx. Now let us consider another case. Case number 2, non-homogeneous differential equation. When p and q are constants and we have a non-homogeneous differential equation with constant coefficients, the solution becomes y is equal to e raised to power minus a1x integration of e raised to power a1x into a2 dx plus ce raised to power minus a1x, which is further equal to ce raised to power minus a1x plus a2 divided by a1. Now let us consider another case, case 3, which is called the general case. When p and q are functions of x and we have the general case, the solution is dy by dx plus 1 by x whole into y is equal to x, and y is equal to e raised to power minus 1 nx integration of e 1 nx into x dx plus ce raised to power minus 1 nx, which is equal to x square divided by 3 plus c divided by x. Now friends, let us have a look at linear differential equation of second order with constant coefficients. This type of equation is expressed by d raised to power 2y by dx raised to power 2 plus a1 dy by dx plus a2 into y, which is equal to f of x, which is our equation number 1. The solution is obtained in 2 steps. Step 1 is to set f of x equal to 0 and solve for d raised to power 2y divided by dx raised to power 2 plus a1 dy by dx plus a2 into y equal to 0. This will be our equation number 2. This is called a homogeneous equation, and the solution is called the complementary function for equation 1. Let this be represented by yc. Step 2 is to find a particular solution of equation number 1. Let this be yv. Then the general solution y will be y is equal to complementary function plus particular function, which is nothing but equal to yc plus yv. Now friends, let us have a look at indefinite integrals. The problem of computing areas under the graph of a function f leads to the problem of finding an antiderivative of f, that is, a solution capital F whose derivative is small f. We follow the usual practice and call capital F an indefinite integral of small f. We use symbol for an indefinite integral of f. We use integration of f of x dx. If two functions have the same derivative throughout an interval, then it must be differentiated by a constant. So, we can write integration of small f x dx is equal to capital F of x plus c when f dash x is equal to f of x. This will be our equation number 1. Now, let us take an example. Integration x cube dx is equal to 1 by 4 x raised to power 4 plus c, because the differentiation of 1 by 4 x 4 is equal to x cube, where bracket denotes differentiation and the symbol integral is the integral sign. The function f of x appearing in equation 1 is the integrand and c is the constant of integration. The dx part of the integral notation indicates that x is the variable of integration. Let a be a fixed number which is not equal to minus 1, because the derivative of x raised to power a plus 1 divided by a plus 1 is x raised to power a. Integration of x raised to power a dx is equal to 1 by a plus 1 whole into x raised to power a plus 1 plus c, where a is not equal to minus 1. This very important integration result states that the indefinite integral of any power of x except x raised to power minus 1 is obtained by increasing the exponent of x by 1, dividing by the new exponent and then adding the constant of integration. Now friends, let us have a look at some general rules. Two rules of differentiation are differentiation of a fx is equal to a differentiation of fx, and differentiation of fx plus gx is equal to differentiation of fx plus differentiation of gx. They immediately imply the following integration rule: constant multiple property. Integration of a f of x dx is equal to a integration f of x dx. A is a real constant here. The integral of a sum is the sum of the integrals. Let us have a look how. Integration of f of x plus gx whole into dx is equal to integration of f of x dx plus integration of gx dx. Repeated use of the above properties yields the general rule. Integration of a1 f1 x plus so on till a(n) fn x dx is equal to a1 integration of f1 x dx plus so on till a(n) integration fn x dx. For the indefinite integral of any linear combination of continuous function. Now friends, let us have a look at the definite integral. Let f be a continuous function defined in the interval a, b. Suppose that the function f is a continuous in a, b and has a derivative satisfying f dash x is equal to small f x for every x belongs to a, b. Then the difference capital F b minus capital F a is called the definite integral of f over a, b. This difference does not depend on which of the infinitely many indefinite integrals of f we choose as the capital F. The definite integral of small f over ab is therefore a number that depends only on the function f and the numbers a and b. We denote it by integration of fx dx in ba as interval. This notation makes explicit the function f of x we integrate, which is called the integrand, and the interval of integration a b. The numbers a and b are called respectively the lower and upper limits of integration. The letter x is a dummy variable in the sense that the integral is independent for its label. For instance, a integration of f of x dx within limit ba is equal to integration of fy dy in ba is equal to integration of f epsilon d epsilon ba. In many other mathematical writings, the difference capital Fb minus capital Fa is often denoted by capital Fx limit ba or by f of x limit ba, but limit ba f of x is also common, and this is the notation we shall use. Thus, definition of the definite integral. Integration of f of x dx ba is equal to limit ba f of x is equal to capital Fb minus capital F of a, where f dash x is equal to f of x for all x belongs to a comma b. The definition does not require a to be less than b. However, if a is greater than b and f of x is positive throughout the interval ba, then integration of f of x dx in limit ba is a negative number. Now friends, let us have a look at some properties of the definite integral. From the definition of the definite integral in the box, a number of properties can be derived. If f is a continuous function in an interval that contains a, b and c, then integration of f of x dx ba is equal to minus integration of f of x dx ab. Integration of f of x dx ab is equal to 0. Now friends, let us have a look at economic application of integration. The integral has many important interpretations. For example, we are led to a definite integral when we want to find the volume of a solid of revolution or the length of a curve. Several of the most important concepts in statistics are also expressed by integrals of continuous probability distributions. Some of the examples are discussed here, which shows the importance of integrals. Extraction from an oil well. Assume that at time t0, we start extracting oil from a well that contains k barrels of oil. Let us define x with respect to time t equal to amount of oil in barrels that is left at time t. In particular, x of 0 is equal to k. If we assume that we cannot pump oil back into the well, then x of t is a decreasing function of t, which is time. The amount of oil that is extracted in a time interval will be t comma t plus delta t, where delta t is greater than 0, is xt minus x bracket t plus delta t. Extraction per unit of time is therefore xt minus x bracket t plus delta t divided by delta t, which is equal to xt plus delta t minus xt by delta t. If we assume that xt is differentiable, then the limit as delta t approaches 0 of the fraction bracket asterisk is equal to minus xt. Letting ut denote the rate of extraction at time t, we have xt is equal to minus ut with x0 is equal to k. The solution to the initial value problem is x in time period t is equal to k minus integration u bracket zeta d zeta in time period t o. If we check the equation first, setting time period t equal to 0 gives x in time period 0 equal to k. Moreover, differentiating the equation yields x differentiation in time period t is equal to minus u in time period t. The result can be presented as the amount of oil left at time period t is equal to the initial amount k minus the total amount that has been extracted during the time span, which is 0, t, namely integration of u zeta d zeta t o. If the rate of extraction is constant with ut equal to u bar, then the result will be x in time period t is equal to capital K minus integration of u bar d zeta in limit t o is equal to k minus limit u bar zeta in limit t o is equal to k minus u bar t. In particular, we see that the well will be empty when k minus u bar t is equal to 0, or when t is equal to k divided by u bar. Now friends, let us have a look at a country's foreign exchange reserves. Let Ft denote a country's foreign exchange reserves at time t. Assuming that F is differentiable, the rate of change in the foreign exchange reserves per unit of time will be Ft is equal to F dash t. If Ft is greater than 0, this means that there is a net flow of foreign exchange into the country at time t, whereas Ft is less than 0 means that foreign exchange is flowing out. From the definition of the definite integral, it follows that f in time period t1 minus f in time period t0 is equal to integration f in time period t dt limit t1 t0. The above equation measures the change in the foreign exchange reserves over the time interval t0 t1. Now friends, let us summarize today's session. In this session, friends, we have learned about the meaning of differential equations along with the meaning and form of ordinary differential and partial differential equations. Moreover, different classification of differential equations and economic applications of integration has also been discussed. Thank you, friends.